Good afternoon, this is Schweitzer. We're going to do a little video here on thermodynamic equations. I already kind of mentioning these things a little bit that, how much energy does a actual chemical reaction give off? Again, that's kind of like I had mentioned in the past, or sometimes I'll mention that you're eating a piece of pizza, and how much energy does a piece of pizza give off? Well, I mean, really, it depends, how many pieces of pizza you eat. If you eat one slice pizza, you get X energy. But if you eat three of these things, then you're going to get three times as much energy. And if this is X, you're going to get X and X again. You're going to get 3X. So every time you cycle through a reaction, how much energy you're going to give off depends on how much you put through that cycle. Um, so a thermodynamic equation indicates the chemical reaction, and then it indicates how much energy is being given off in that chemical reaction. Now, first of all, you have to be balanced. So when I balance this thing, there are several ways you can balance it. So I could take this guy and balance it, and we get 2 and 2, 2. So we need a 2 here, and then we need a 2 here. Now that's balanced. And that means for our thermodynamic equation is we have a delta H on the end. Okay, and just a reminder that if it's a negative delta H, that means that we are exothermic. Another way to do that is to say plus energy on the product side, which means energy is being given off. The question is how much energy? Energy is just symbolized by Q sometimes. So if in this case, delta H is the amount of energy given off by this chemical reaction. More specifically, it means 2 moles of this, 1 mole of this, and 2 moles of this guy. So that means, like if you look at the molar mass of this guy, the molar mass of hydrogen is 2 grams per mole. This guy is 32 grams per mole, and this is 18 grams per mole. So we typically, although you don't have to, we typically use it in a mole ratio, energy per mole. So that means that 2 moles will give me X amount of energy, okay? And, in that case, 2 moles happens to be 4 grams. 2 of these is 4, 2 times 2 is 4. So these are all just ratios. It's all one linear relationship. 4 grams of this requires 32 grams or 1 mole of oxygen. You can't get away with having 4 grams and 30 grams. That has to be for this reaction. Another example might be if we were to take, okay, what about this, where we have 1 mole of this, okay, then we have a half a mole of this guy, and we get 1 mole of that. This is also a balanced equation. So this one here is going to be 2 grams, because that's 1 mole. So 1 mole, okay, a half a mole, all right, and then this is going to be 16 grams. And then we have 1 mole, which is 18 grams. So, of course, here again, we're going to get 18 grams here, and which is 1 mole, and this guy is 2 moles, which is 36 grams. Of course, adding those two up. So in this case, what's delta H? Well, we can always think of it in terms of one item or both or whatever, but in this case, to process 1 mole of hydrogen through this, is the delta H for this reaction is negative 285 kilojoules. That's just what I looked it up. That's just what it is. Now, they don't always put per mole on here because everything's got different moles. It really is, they'll say per, sometimes they'll put per reaction. Cycle. One cycle through this reaction of this 1 mole, half mole, 1 mole gives me that much energy. So if I put 1 mole of this through, I get that much energy. If I put 2 moles through, I'll get twice that. Okay, and that happens to be this one. Okay, so if 1 mole gave me 285, and 2 moles is going to give me twice that. So 2 times 285. 2 times 285 is 570. So that means this guy right here is negative 570 kilojoules per mole. Okay, and it's just a proportion. Now, let's run through this. Now we know here that 4 grams or 2 moles gave me this much energy, and of course 1 mole or 2 grams gave me this much energy. Those are proportions. Okay, so here says how much energy is released if 1 gram of hydrogen is burned. Now we're assuming there's excess hydrogen here. Okay, this is my standard, what I would call stoichiometry for thermodynamics. So for this, really all factor label is just proportions. So I don't know how much energy 1 gram gives off, but I do know that 2 grams gives off 285 grams, kilojoules of energy. So a linear proportion is just this. And some kids like to go back to this. I don't know how much 1 gram but it gives off, but 2 grams gives off 285 kilojoules of energy. Now the negative just means the direction of flow, which means it's exothermic. So it's up to you how you want to deal with that negative. So what would 1 gram give me? And at that point, you just cross multiply and divide. That's the standard ratio, which almost all chemistry. But in this situation, there's another way that we'd show this with factor label, which is more common. So if I have 1 gram of H2, I want to get rid of grams, and I want to go to moles, because typically reactions run on moles. I want to get to a point where I can use my delta H as a ratio. One of those two, doesn't matter. 1 mole equals 2 grams. That's what hydrogen is. And then I want to get rid of moles, and I want to go to kilojoules. This right here is the delta H. So it wouldn't matter which one we use, okay? But the top one is 2 moles gives me 570 kilojoules of energy, and the negative just means it's being released. I could have put 1 over 285 as well. The 1's this guy, and the 285 is here. The 2 here, 2 moles, gives me that much energy. That's the delta H, and that's going to give me my energy. Of course, you know if 2 gave me 285, 1 should give me half that, but you can run the math through as well. So at this point, 1 divided by 2 is 0.5, and I'm going to multiply times 570 divided by 2 equals 142.5, which is exactly half of the other one. So 142.5, and that's kilojoules of energy. Okay. Now, here's again just another example. You should try this one. Pause the video, see if you can get this to work out. Really, it's pretty standard math. Something you can have on a note card, or if you don't want to memorize it, but it's just your straight up stoichiometry. You could reverse this and say, I need X amount of energy. How much would I need to burn, too? You could reverse it around. But this is pretty common. I got 50 grams. All right, dot line, get rid of grams, go to moles. 1 mole is 2 grams. Dot line, I want to get rid of the moles and go to kilojoules. Okay, and this is, you could use the 1 to 285. It's not the one I used last time, but it's the same ratio. You also could say, now you can go ahead and solve this out. Let's just run that math quickly here, so you get an answer in case you're trying it. 50 divided by 2 times 285 is just 7,125. So 7,125 kilojoules of energy. So I also could do something like this, where how much energy would be released if I were to produce, 50 grams of water. Same exact scenario here. I made 50 grams of water. How much energy also got produced? Well, for every 1 mole of water that's produced, 285 kilojoules of energy also produced. So I would just do it this way. 50 grams, get rid of grams, go to moles. 1 mole is 18 grams. And then get rid of moles and go to kilojoules. And it wouldn't matter which ratio you used. I can use the 1 to 285 or 2 to 570. Okay? And I flipped them back and forth. I go 2 to 540, 570. Okay, and that would give my answer. This divided by, multiply gives you your answer. That's pretty much it. That ends our discussion on thermodynamic equations. Thank you.